When we drive a car at 60 km per hour and there is a truck coming from the opposite direction at 30 km per hour, we see it approaching us at 90 km per hour. The law of velocity addition works here. Let's denote speed of light with c. Imagine an observer moving at speed v towards the source of that light. It would seem that the observer will see this light as coming with speed of c plus v. Nothing of that sort. Many experiments were carried out at the end of the 19th century, which showed that the speed of light measured by everyone, even a moving observer, is always the same and amounts to approximately 300,000 km per second. This is true of a vacuum. Light travels slower when it passes through air, glass, or something else, but in a vacuum it always has a speed of c. This discovery meant that the law of velocity addition was wrong. On the other hand, it was difficult to abandon it since it worked in so many other situations. Einstein tried to find a new theory that would reconcile the observations of light with the old laws of motion known from Newton's time. He made two assumptions. First, the speed of light is constant for every observer. Second, that in all inertial frames of reference, the laws of physics have the same form. A reference frame is called inertial if the observer doesn't experience acceleration. And by acceleration we mean any changes in the velocity vector over time, even if only changes in direction. So a system moving in a circle is not inertial, only moving in a straight line at a steady speed or standing still. The assumption that in all inertial frames of reference the laws of physics are the same means that if we sit in a speeding train with a curtained window and, for example, throw a ping-pong ball, the ball will bounce exactly in the same way as if the train was standing still. We'll not be able to tell after its movement whether the train is moving or standing. This applies to all the laws of physics, and therefore not only experiments with the ball, but also with light, radio waves, and others. The theory I'm discussing is special relativity. It's worth noting that Einstein also worked out non-inertial systems and gravity, devoting to them the general theory of relativity. Now let's look at the consequences of these two assumptions of special relativity. A scientist on a fast-moving spacecraft wants to measure how long it takes for light to travel 50 meters. To this end, he extends two arms from the ship in directions perpendicular to the direction of flight, so that they are at a distance of 25 meters from each other. The experiment is to let the light out of one arm, wait for it to reflect off the mirror on the other arm, and record it returning to the first arm. The time elapsed between the emission of light and its return is measured. Since light traveled at speed c and has traveled a distance of 50 meters, the result must be 50 meters divided by c. A second researcher on the ground observes the entire experiment through a telescope. For him, it looks different due to the movement of the ship. The light travels diagonally, so its path is longer than 50 meters. Since, as I said before, the speed of light is c for each observer, including the one on the ground, so it will take a longer time to travel a longer distance. Thus, both observers look at the same events of sending and receiving a light pulse, but for the observer on Earth, the time between these events is longer than for the observer moving with the experimental system. This phenomenon is called time dilation. This formula shows the time in a stationary frame of reference as a function of time in an event-related frame. V is the speed of motion and c is the speed of light. As the speed of motion is small compared to the speed of light, the denominator is very close to 1, so the times in both frames of reference are more or less the same. This is in line with our experience in everyday life, in which time is one and the same for all. However, if the speed of motion approaches the speed of light, the denominator decreases and the observed time increases, going toward infinity as v approaches c. Let's pause for a moment here. Suppose the researcher who is currently on the ship has done this experiment earlier standing on the ground and remembers observing a longer time. Can he then look from his frame of reference and think, I'm standing still and the guy on the earth is moving, so again I should be taking note of a longer time? No, the time is dilated in the eyes of the observer who moves in relation to the observed process. In this case, the process begins with light emission and ends with light detection. Both of these events occur on the lower arm of the ship. The observer on the Earth is moving in relation to this lower arm, therefore he is the one who records a longer time. We have considered time measurement so far, and now let's move on to length. The ship moves with respect to the Earth at a known speed v, which both an observer on the Earth and the ship's crew can measure, except that the crew sees it as the speed of Earth relative to the ship. In order to measure the length of the ship, it will fly past a satellite. A sensor on the satellite will capture the moment the ship begins to pass by and the moment when it ends. Observers on the Earth will multiply the time interval between these events by the speed of the ship to calculate its length. The ship, on the other hand, is equipped with sensors placed at its beginning and end, and the satellite has a point light so that the ship can accurately detect when it's passing by. An observer on board measures the time between the front and rear sensors passing the satellite light. Similarly to his colleagues on the Earth, he multiplies the time obtained by the speed of the ship to calculate its length. Determining whether they both obtain the same length of the ship comes down to determining whether they measured the same time. But now note that in this case time dilation works the same as before. This time the initial and final events take place at the satellite. The researcher on the ship sees the satellite as moving, so he is the one who will record a longer time, and thus a greater length than the one on the Earth. Intuitively, however, it is the observer who rests with the ship who has the most objective view of its length. Then the Earth's observer result must be considered shortened or contracted. Length contraction is the second phenomenon characteristic of special relativity. Since the length contraction is a result of time dilation, the formula is analogous, only this time we are multiplying by the square root instead of dividing by it. Finally, the scientist on the ship changes the configuration of his instruments. In the center of the ship, he sets up a light source and detectors at the front and rear, each at the distance of 10 meters from the source. The researcher emits a light pulse from the source and records what time the light reached each of the sensors. Since the length of the forward and backward path of the light is the same, he will capture exactly the same time in both cases. On the other hand, an observer from the Earth sees it this way. Light spreads back and forth from the source, but at the same time, the whole ship and the detectors are moving. The rear detector heads towards the light and it will therefore catch it before the light travels 10 meters. On the other hand, the front beam of light, even if it travels 10 meters, will not reach the detector that escaped at the time. Since the light traveled different distances and moved at the same speed, the times from sending the light to the individual detections had to be different. Thus, the detection events themselves couldn't be simultaneous. This is another conclusion from special relativity. The fact that events happened in the same time is subjective. We call it relativity or simultaneity. What seems simultaneous when observed from one reference frame, from another it is not. So there's no universal time. For the researcher on the ship, the first detection could take place at 3 p.m. and the second also at 3 p.m. But for the one on the Earth, one at 3 p.m. and the other a nanosecond earlier. things will get even more complicated if you try to apply relativity to cases different than discussed here. Therefore, let's sort out when which of those phenomena occurs. Time dilation refers to the duration of a process that started and ended in the same place in some frame of reference. The extended or dilated time is observed in those frames of reference where the end point of the process is different from the start point. Length contraction refers to measuring the distance between 2 points at the same time. The shortened distance is observed in a system where these points are moving. And non-simultaneity concerns events in different places which are simultaneous in one frame of reference and which are not in every other moving with respect to it.